All right. All right. So as you are probably aware, self-supervised learning and vision language learning is everywhere. I mean, starting from GPT-4 to The Guardian even having their own page related to ChatGPT, to, well, all the kinds of newspapers and the news and the memes and the Twitter that you see. That's all of these things, including GPT and other models, and even stuff like Stable Diffusion heavily relies on methods that come from self-supervised learning. And of course, the main data sets that are showing these sort of gains are vision text or vision language data sets. So in this lecture, we'll be covering a bunch of these things. So first of all, here's just a subset of the model names. They won't mean anything to you right now, but we'll be covering a lot of things. So this is a very advanced lecture in your Masters in AI course. So we won't be talking about optimization or regularization or these kind of basic things. So these are assumed, and these are all used in all of these methods. So all of these methods, of course, use Adam to optimize the loss functions and all of this stuff. So everything you've learned in DL1 is still relevant, but it's sort of in the background now. If you read the papers, you'll see some of the things that we've discussed earlier, but they won't be the main focus. Just briefly, the intended learning outcomes of this course are the following. You've probably seen it in the course description. So it's about understanding what's going on in the large-scale vision language learning domain. It's about what has changed in recent times. Okay. We'll be focusing a bit on the notion of in-context learning, which is sort of this new notion that's emerging, especially from the language domain, but also now in the vision language domain. And finally, these 2 points basically apply to your project. So you can critically analyze and judge scientific publications in this domain after these 2 lectures. And then you can apply these models to your own research and use them in your own code. All right. A brief note about the philosophy. So as I've said, there's a lot going on. So we won't cover all the models. In the end, I hope you'll begin to see the similarities between the different models. So then you will be able to look at the new paper that we haven't covered and say, they do this like that model, do this like that model, and you understand it. So it won't be an exhaustive enumeration, but it's meant to show you what kind of directions there are. And I've achieved my goal if after the 2 lectures you think combining self-supervised or vision language learning is exciting, and the lectures gave me ideas for my own future creative research ideas. That's sort of my main goal here. I want to get you excited about what's going on and inform you about what's going on. And then, of course, if you wish to unleash your creative ideas, there's the master thesis at the end of the academic year. And finally, organizational note, the next and last lecture is 25th April. At some point, there was somewhere I saw 20th April being written, but it's the 25th April. After that lecture, there will also be the tutorial. And then the meetings with the TAs, Ivona and Mohammed, they will happen on the 18th April via Zoom, and then more meetings on demand. Any questions about organizational note relating to this course? Otherwise, ask the DL2 organizers, please. I also know only so much. All right, so we'll start with self-supervised pre-training. You might recognize this picture sort of from the DL1 course. I'm going to give a brief refresher because it's important for everything that we'll cover here. So the question in self-supervised learning is, how do we learn without labels? The answer is sort of, we need to generate a loss that provides gradients, that doesn't require any human annotations. So there's a couple of methods. We've covered a bunch of them in the first course. Here I'll focus and explain a bit more in detail contrastive learning, which is sort of a signal that comes from assuming an image is unique and assuming that if you augment an image, it will stay the same, or the meaning shouldn't change. And this other approach of reconstruction, which we call masked image modeling. So modern contrastive, noise contrastive learning sort of emerged from this work, non-parametric instance discrimination, in 2018. And after that, what really made it big is the work SimClear from Google and Jeffrey Hinton and so on. And that's what we're going to look at in a bit more detail. So, right. So it works as follows. So you first sample your badge by taking images. In this case, you can see 2 images of a cat and 2 images of an elephant. They're both coming from the same image. So they're just augmented version of these images. And let's say your badge size is 2, or in this case 4, because every image is augmented twice. The next thing you do is you push them through the neural network. And then after that, you get a dense vector out. These dense vectors, you compute the similarity. So how close are the vectors together? So you can imagine them as being points in some n-dimensional feature space, and you sort of compute the L2 distance. Or if you normalize these vectors to lie on the unit sphere, you can simply compute the angle between the vectors. So that also tells you how close they are because they cannot vary in length. And the angle is equivalent to just computing the cosine similarity, which is also described below. There's one more quirk sort of here, which is this temperature parameter tau. This basically increases or decreases the values that you get. So it's just a scaling function, essentially. What you then try to do in the sort of pretty much last step is you try to relatively increase the similarity for the pairs. So in this case, you will try to increase the cosine similarity for the images that come originally from the same image. And you try to relatively decrease the rest. The question is, of course, why do we have this relative here? What happens if you only try to increase the diagonal? Any answer? All right, I'll need to get warmed up, but yes.
Then it wouldn't be augmentation.
Invariant?
Sorry. Yeah.
It would be. Let's. Yeah.
Only increase those, they would be only similar to themselves, right?
If you increase the diagonal, that would mean every image is at least the same compared to its augmentation. But if you just do that, it could map everything to a 0 vector, let's say. And then if you don't care about these off diagonals, it would collapse into some trivial solution. Thanks, you probably knew the answer. Gonna keep it brief. All right, and then of course, this is sort of how it's shown in the paper, that basically you take this image and these 2 features, they attract. So that's what we say with trying to make the diagonal or like these pairs high value, and the other ones repel. And you do this with a softmax function. So that's what I mean with relative. So you can only achieve a high value in this similarity matrix by having low values in the other ones. That's essentially how softmax works, because softmax needs to add up to 1, right? I hope this is all nothing new to you. It's just a refresher. And because there's no, your batch size could be 16,000, which is typical values. But your vector dimensionality, so the space of the cosine similarities and so on, that could be, let's say, 400 or something. But still, you're doing a softmax over 16,000. So that's why we call it non-parametric softmax. It's not like you have a fully connected layer that's 16,000 sized. And now we understand this. So it enforces image uniqueness because it tries to push everything apart, and enforces augmentation invariance. So it pushes 2 augmented images together. All right, so that's the part that we need to know from self-supervised contrastive learning. Now we go to language modeling. This is a nice XKCD comic, and we want to basically understand why we perceive it as funny. By the way, erudite sort of means highly educated or something. It's a rare word, and that's sort of the point. Given the context, the word erudite is quite rare, especially given the context. I mean, if you read Shakespeare, maybe erudite might be frequent, but especially if you read everything that's come so far, erudite would be extremely unlikely. And so basically language modeling puts this into a self-supervised task. So what they do is they factor the probability of a data point. In this case, the data point is a sentence. So a sentence contains word 1 all the way to word n in the following manner, that the probability of a single data point of a sentence is simply the probability of the first word times the probability of the second word given the first word. That's this term. and times the probability of the third word given the previous, and so on. And overall, you can write it, of course, in a very simple manner in this product form. Put more simply with an example. So here we're trying to calculate the probability of the sentence, and it's simply given by starting from the first word, probability of where, times the probability of given where, and so on and so forth. And if we're trying to predict the probability of the word going, then what we call the previous words, we call context, because that's exactly what it is. It's the context that we already know, and we're trying to predict the next word. And in this case, the context was, oh my God, the volcano is eru. And then the question is erupt or erudite. And indeed, if you check it, these are Google searches. If you check the, oh my God, the volcano is erudite, has I think 300,000 matches, 600K, and oh my God, the volcano is erupting has 3 million. So indeed, it's correct, and it's probably just inflated because of the XKCD comic anyways. But that's pretty much it. Like now you can, if you enumerate all the other things that end with eru, and you get the count from Google, and then you divide it all up to get a number between 0 and 1, that's pretty much what you should get in a good language model. And that's what the language model is trying to do. All it's trying to do is predicting the next word. Now we can make this a bit more specific, and we make it specific with the GPT architect or GPT model. GPT wasn't the first language model, and a language model is simply a deep neural network that acts on words as inputs or sentences or letters, you could even say. It wasn't the first to use this as their objective. So predicting the next word has been around for a very long time. But we'll focus on GPT for the obvious importance in the field. This is taken directly from the GPT paper, and you recognize what you've seen before. In this case, we have U and not a W. So in this case, we're not predicting directly words, but tokens. So that's why U and W, they're similar. It's just a word that's further changed with a neural network, essentially. Theta are the parameters, and K is the context, as you can also see in the legend here. N is a number of layers and so on. And you start first by embedding the words in a vector that gives you sort of this first representation. And then afterwards, you just throw a couple of transformer blocks at it. And then you want to predict what's the probability of the next word. I don't know why it does that, by the way. If you want to predict the next probability of the word, you just do one softmax across your vocabulary. Typically, vocabularies, I think in this one was like 30,000 or something. So it's a pretty big softmax. But yeah, that's how it is. In practice, what we call this context, especially if we go from left to right, causal. So because this mimics how we read. Obviously, a machine wouldn't have to do this. And so you also see things like non-causal masking, which, for example, involves predicting the middle word of a sentence or predicting multiple words in the sentence. And then your context has to be sort of the future and the past in a way. And yeah, there's different approaches. The nice thing, of course, if you train it in a causal way, and I'm sort of going ahead of myself, but why do you want to do this? It's because then if you want to predict sentences, you just predict the next word, you put that as your input, and then you predict the next word, next word, next word. So you generate sentences. If your model can only fill in the blank, then you need to start off with a blank and then it fills it and that's it, right? So that's why next word prediction is great. Yeah. All right. So GPT 1, 2, 3. Same loss, different training data, model sizes, and slightly different architecture. But basically, GPT relies on the transformer decoder architecture. So it's all decoder. It doesn't have the transformer encoder, if you remember lecture 7 from year 1. GPT-1 had 117 million parameters, 1.2 gigabyte size data set, and they trained it, and then they used supervised fine-tuning for downstream tasks like sentiment classification and all of these sort of things. And I think there were only 4 authors on the paper, and now GPT-4 has like hundreds. Fun fact. In GPT-2, they already went to 1.5 billion parameters, which was already considered big at the time. The training data set was also fairly big. often fine-tuned to perform specific tasks afterwards. And smaller versions were released. They had this sort of staged release of first releasing small models because they were worried about fake news. And of course, now we have GPT-3 being quite popular, which then moved the needle to 170 billion parameters, showed that it's quite capable of doing all kinds of things. The training data set they had used was 570 gigabytes of web pages, books, articles, websites, and so on. And they started off with, I think, 20 terabytes initially and filtered it down to get a high quality training data set, which is proprietary. By the way, this is a common theme now that for these really large and important, in quotation marks, models, their training data remains sort of hidden. We'll go to the training data at the very end of this lecture series. But and yeah, then GPT-3 had some really strong new capabilities. And we're going to focus on one in particular, which was so surprising in a way that it made it into the title, right? The paper is called Language Models Are Few-Shot Learners. The paper isn't called GPT-3 bigger and better than GPT-2, but it's called Language Models Are Few-Shot Learners. Obviously, the other sentence I mentioned is quite true, but what do they mean with that? So what they mean with that is it can do few-shot learning. So instead of it just asking what is the word cheese in French, you give it first a couple of examples. So first you describe the task as you would to a normal person, and then you give it some examples, and then you ask it, okay, so what would cheese map to in French? And it turns out that this works much better than simply asking the model to translate it, which is in a way weird because you're simply asking the model to retrieve knowledge that's stored inside its weights. But if you provided a couple of examples, it seems to work a lot better. And we call this emerging capability of large language models. And first of all, we call this in-context learning. In this case, we're using the term context as all of this, right? And we're providing inside the context, we're providing the task and examples. So within this context, it needs to figure out what it needs to do, and it needs to solve it for the given query. And all of this during a single forward pass. So you simply provide this to the model and it outputs the solution. You don't fine tune the model. And this is a big theme that we're going to see over and over. You train models, you train large enough models, and then you can apply them for all kinds of things without further updating the weights, without any gradients. And this is, by the way, a really big opportunity for us, for academia, because we mostly cannot train these huge models, but we can do forward passes. That's no problem. We can have access to the GPT-3 or 4 APIs and all of this stuff. We're going to talk more about in-context learning later. For now, I simply wanted to show you the evidence of this. So in this case, you see the number of examples in context. So at 0, we just simply have basically translate cheese into French. And that gives you like a fairly bad performance. If you add more and more examples in the context, you can see that the performance continuously increases. What you also can see is that the performance seems to increase much faster and much faster really for the bigger models. So that's the difference between the different colors. Yeah, as you can see here. So with the green model, it performs better if you give it 50 examples compared to no examples, but it improves very slowly. But for the 175 billion parameter model, you give it 50 examples and it pretty much seems to have figured it out. And that's why the paper is called Large Language Models Are Few-Shot Learners. Any questions so far? Yes?
Do they also do something of the sort then that you enter a prompt and then they try to do some prompt engineering on the back end to improve your prompt further more, to give it more context? So for example, you ask a question about coding, they classify it as a coding exercise or question. And then they say like act as a software engineer, blah, blah, blah.
In the normal GPT-3 variant, no. Also this act like that's more something that is for ChatGPT. It really depends on how the model was trained. There is, in a way, the model does this implicitly, right? By saying like, okay, now we want to translate something. It sort of uses its translation trained neurons in a way. If you say, now write the story about something, or now recount the facts of the French Revolution, it uses different parts automatically. So that's kind of the nice part. In a way, you don't want explicitly a human telling it, now switch on your coding abilities, now switch on that. At the same time, of course, GPT-3 has been released, and then they fine-tuned various versions of GPT-3, for example, one version on code, one version on other things, and so on. So tailoring these models definitely has advantages. Like, for example, there's a financial company called Bloomberg. They also trained their own GPT-3 model and finally tuned it on their own data. So yeah, there's something there. Yes?
Because this is called few-shot learning, but it needs to have seen the translations before, right?
Those are the few shots, yes.
Yeah, but it's not learning from the examples. This is kind of a way to prompt it to retrieve that knowledge it already has, that cheese is fromage or something.
Yes, but yes, yeah, you're completely right. Like, if we define learning as updating the parameters, yes, but because we see this increasing curve with more examples, we call it learning. In a way, you could call it better prompting that achieves the task, but yeah, we call it learning. And yeah, that's pretty much it. Yes. Yes.
How much data would you actually need to fine tune something like that? I mean, if it's been trained on 570 bytes, assume in order to actually have an effective fit.
Oh, you can fine tune it with a single sample if you wanted to, but it wouldn't work. So the question is, it depends really. So we'll go to adaptation methods at the end of the lecture. So you can fine tune the whole model. That requires a lot of GPUs, which you probably don't have. You can fine tune only a part of the model, and there it becomes a bit. Generally, OpenAI also offers an API where you can fine tune a model, I believe. But yeah, there's no hard and fast rules. Yes.
When you say in a zero shot case, or when there are zero training examples in context, accuracy is low. In fact, it's showing 10 or something.
Yeah.
Are we saying is the poorly designed prompt in this case, or asking it directly what is the translation of cheese and French? Is it still going to give us bad results 9 out of 10?
Both. So the few shot capabilities, they're quite true. So if you provide more and more, it simply works better. But this was sort of the first paper that did it. Indeed, like, there's better ways to ask a model zero shot. For example, if you ask it who was president in the US in 1973, it might get it right or it might get it wrong. But if you ask the model in a different way, and we'll go to that later, it achieves much better performances. So that's where all this prompt engineering came in. All right. This slide I'm not going to go through in detail. ChatGPT basically takes GPT-3 and then fine-tunes it based on human preferences. So there's some humans involved in there, which first provide ideal answers. Then you train a model that recognizes what are ideal answers. And then you have humans again in the loop, which rate different answers, basically. And that's what we've been all testing out and so on. And we don't know the exact details of, let's say, how big the data set was, etc. But OpenAI released this paper called Instruct GPT, which contained the basic ideas. And that's why we sort of know roughly how ChatGPT was trained. And then, of course, we have GPT-4. It's bigger and better. And apart from that, we don't know anything. So there's some estimates which say it's between 500 billion and a trillion. Probably a trillion, because it just sounds nicer, but who knows? And yeah, so this is a lecture. It's not a marketing commercial, so I'm not going to talk much about it. The only thing that I want to mention is GPT-4 now has language and vision capabilities. And instead of talking about this and speculating what it's doing, we're going to talk about other image and language models in a bit. And of course, I should mention that there's a lot of different language models out there as well. So there's notably importantly for us in academia, there's Llama, which has been released in a couple of different sizes, is freely available for download, even though it's one of the best language models you can get. And they even released the 65 billion parameter model, which is huge for us. But there's other versions as well of language models, for example, that have been fine-tuned on instructions or fine-tuned on code and all of these sort of things. All right, so then there is another, well, just basically now going back from language back to images. So you can sort of apply something similar to images. So instead of masking words or next tokens, we simply use image patches. Just because now in Vision, we also have a transformer architecture. So this seems like a straightforward approach. And this has been making a lot of progress and actually gives you the best kind of pre-trained models if you fine-tune the models afterwards. And it scales decently as well. But something to think about is that in language, the words represent the sort of undivisible parts, or at least the tokens, undivisible parts of language and have meaning. But the individual patches don't carry necessarily meaning. So it isn't quite the same, right? Especially because language, the output of language is quite vast. Once it can generate language or understand language, it can do all kinds of things. With these sort of models, yeah, you can ask it to fill in the blank, but that's pretty much it. Or you can even make a model that starts at top left corner and then fills the rest of the picture. Those models have been around for a while, called Pixel CNN or Pixel RNN and so on. But they won't allow you to do anything that's beyond just creating an image. Because yeah, the output of this model is just pixel. So one thing to think about is what is like GPT models are quite fundamental and you can do all kinds of new things with them, but not quite for these sort of masked autoencoding models. All right, so then we'll go to multimodal learning. So here the modalities or sensory perceptions that we as humans have. There's also orientation, I believe, like if you tilt your head and all of that stuff. And I've added manually captions and thoughts in a way, just because if we think about multimodal learning in deep learning, we have vision, which is pixels, and then we can treat text as a separate modality. And that's mostly what we do. So those pictures just motivating. What modalities do we deal with mostly in deep learning? So the general rule is anything that's not nailed or that's not locked on the internet. So everything has been not everything, but a lot of things have been downloaded and used. And deep learning, what we know is it scales with data. So there's a bunch of large data sets, mostly of images and text, but also of speech and audio, and recently also of LiDAR points, obviously important for self-driving cars, or generally more 3D models are getting important with the metaverse and all of that stuff. For multiple modalities, we have the one that's been dominant up until a few years were videos, because videos provide you not only these RGB pixels, so the frames, but also audio. And if in the audio there's someone speaking, you can transcribe it with some automated system. And then you have pixels, you have words, and you have audio. And audio you can represent as a spectrogram or whatever. And I've been doing some research in this domain and sort of now doing a lot more research in the image text domain because of the language part. And we'll go to that part. But the typical data in the image text domain are simply images with captions or images with alt text. So that's if you go to a website and you hover over the image, sometimes you have a description of the image, or on Twitter, sometimes people write alt text to help people with seeing disabilities know what's in the image, for example. So what makes multimodal learning interesting? In the example of vision language. So for the example of audio and video, I've shown you the McGurk effect, if you remember. I'm not going to show the video again, don't worry. In the example of vision language, we can, for example, first of all, treat text like an augmentation. That's simple, right? Like if you look at the caption, you pretty much know what's going on. You don't know if the grass is very green or not very green, or if the picture is, well, the batter is left-handed or right-handed, but you pretty much know what's going on. So it's almost like an augmentation or like some higher level description of it. That's nice. So augmentations, we know, help a lot in deep learning and are quite fundamental. Another point why vision language is nice is there's some settings where you need more modalities. So in this case of this meme here, you won't understand the true meaning of it unless you read it and you look at it, basically. And this picture is taken from the Hateful Memes Challenge, where basically Facebook made a synthetic meme data set, or like a made-up meme data set of these sort of memes, where you need to understand both modalities at the same time to be able to determine whether it's hateful content or not. And the other example I sort of came up with is, if you look at this, you don't know, let's say that you weren't able to see the top lights, you wouldn't know if the ambulance car is in emergency mode or not if you don't hear what's going on. Although probably hearing it would be enough in this case. But another example is that text descriptions, contrary to the caption example, could be very detailed. So in this case, you can see, for example, right. So you can see this really detailed text. And furthermore, you can see that this person, this is a very short video, but you can see that this person is also pointing where the text is. So when the person talks about the blue sky, they're pointing in the blue sky part. When they talk about the balloon, they point to the balloon and so on. And there's this data set, for example, with almost 1 million images with such descriptions, with the audio of someone talking about this, with a transcription, which then is the caption, with a pointer. And a part of this data set also has semantics and segmentations. So like you would have the person, a box, or like a full segmentation mask around the person and all of that stuff. So these data sets can be quite detailed. So it's no wonder that you can learn a lot. But the main reason why the language part is so desirable is because language is quite generalizable. So we've seen that from language models. You train them to simply predict the next word, and it can write a story in the style of Shakespeare, or it can write a poem or whatever. Language is super nice because it's a universal format for posing and solving tasks. It obviously has the advantage of being human understandable, and happens to be that large enough language models are few-shot in context learners. So language models provide a whole wealth of opportunities of what we can do. And also from the GPT and other papers, we know that language models seem to scale really, really well and predictably with scale. So you can pretty much know how good your model is by simply calculating how much compute, how much GPUs, how much data, and how much time you're going to throw into your training run. You pretty much know exactly how good your model will be. So they're very predictable. And it's not like doubling the data improves the model by 2, but it's more like a power law. So every time you want to achieve a 2% increase in performance, you need to double your data or something like that. So it's quite expensive to improve them at the larger scales, but at least they're predictably scalable, which is a very desirable property. Right. CLIP is one of those first vision language models which became really, really popular. CLIP simply takes what we had in SimClear and applies it to the different modalities. So in this case, instead of augmenting the other sample in quotation marks, it simply uses the image caption. And you have a text encoder. So the text encoder produces a vector out of the caption. And then you take these 2 vectors, compute the similarities, and train it in a noise contrastive manner. And you pretend like there's no other caption that's very similar in the batch. You pretend like there's no other similar image in the batch. And that works well enough if you have a large enough training data set. In this case, their training data set was 400 million image text pairs. We don't know which ones. We know they're probably pretty good because people have been trying to reproduce it, and they needed a lot more pairs of noisy data to achieve similar performances. But you can do some good things with them. And I'm going to start, I think, starting from this slide, adding some links where you can try these models. And in this case, this is actually one of the official ones. There's also unofficial repos where people reproduce models, and they work sometimes almost as well, sometimes not quite as well. But there's some companies like, for example, DeepMind, which don't release many models. So then people in the community train them. Sometimes these are efforts across multiple universities and institutions, and then they release these models for people to try out. In this sort of demo, what you can try is you can simply supply all kinds of words, all kinds of images, and you can figure out which properties belong to which word or which caption belongs to which image. And this one would be, for example, if you have different kinds of properties, like skyscraper, bus, boy. Well, these are mostly just objects, but as you remember from the assignment, you can also use properties like green or night image or photograph or comic, and you can figure out what you can do is basically you can do zero-shot classification. So in this case, zero-shot, the model hasn't been explicitly trained to classify whether the image contains a red or green object, but because red and green, the text model can understand because it somewhere in the training data has seen a very green pasture in a cow or a very red ball or whatever, these sort of things. It sort of knows how to associate red and green. So then you can do red and green classification, even though the model hasn't been trained for that. And that's only because you have a language model that's very flexible and can understand these things. And a language model can also know in quotation marks, but can understand and associate red is similar to chimney colored, is similar to peach colored, and all of that stuff. It won't know it perfectly. Like, for example, if you compute the language embeddings of all the numbers, you can see that, for example, 25 is closer to 20 and 15 compared to 21 sometimes, because it simply doesn't embed it in the natural way. It just goes by correlations. So, I mean, maybe for the 20 example, that's not the case, but for other numbers, just because 15 and 20 occur more frequently together than 20 and 21, or multiply that by 100, and then you get a slightly more realistic case. But all right, are there any questions here? All right, also let me know if I'm going too fast or too slow. All right, then one follow-up work, this time from Google, on the CLIP model is the lit model. You'll see a bunch of more funny names in this lecture. They also had this burn emoji in their title, by the way. So this paper is called Locked Image Tuning. And what they simply do is they have these different encoders. So they have the image encoder and the text encoder. And they test out different things. So if you start from a pre-trained image model, in this case, a very strong self-supervised one, or supervised one, works either way. And then you train these models to in a contrastive manner like CLIP. So what you do is you try to align the different modalities in this joint embedding space that you have in CLIP, right? So yeah, or even in SimClear. This is the joint embedding space, right? This green and violet part. They both are vectors that live in the same space. They live in the same space because otherwise the similarities you won't be able to compute them if the dimensionalities are different, and you won't be able to have high similarities if they're not in the same space. So yeah, starting from these pre-trained image models, how can you best align these models to end up as good vision language models? And what they find is that actually the image models nowadays are good enough. So you can simply log them. So you don't need to provide any gradients for the image models. just keep them frozen, just train like an MLP or linear layer on top that does the matching from the image embedding that you get out of the frozen image model towards the joint embedding space, and the text model you simply keep training. And you find out that, yeah, locking the image model is a lot better. They provide some reasons for it. One of the reason is that these self-supervised image models tend to be, or generally image models tend to be already quite good enough. And if you fine-tune them on this text image task, they might degrade. And the reason for this is that in this paper, they use a smaller data set. So if you simply use, obviously, CLIPS 400 million, you don't have any degradation of the image encoder because they trained the image encoder from scratch. It sees 400 million images. It's obviously very good. But if you have a smaller data set of, let's say, 3 million or 12 million image text pairs, and you fine-tune your image encoder on that, and the text pairs are quite noisy, it's not going to work as well. So you simply lock the image encoder. And what's nice, of course, is if you lock the image encoder, you just get the embedding for every image once and you store it. And after that, this stored vector becomes your new image, so to say, your new input. And that's why you can easily, in quotation marks, use a giant image encoder. So in this case, recently a paper came out that is a vision transformer with 22 billion parameters. So previously vision models have been up to 1 billion parameters. So this is like the biggest vision model out there yet. So you cannot easily update this model or add gradients or whatever. But if you simply do a forward pass, save this vector as a database, and then pretend like those are your image inputs, you can actually do this quite easily. And so I give it a small well done mark in this case. And I'm going to add these in the next slides. So this well done mark is like, how little compute can you use? I think they used actually 8 TPUs or something, which yeah, is still a bunch for academia, but it's definitely doable. All right, so next we're going to talk about combining the GPT models and some more. But I think we're going to take a short break now. Let's say until, yeah, until 5 to, so 10 minutes.
Hi.
Hi.
I have a question. So I was
Yes.
playing around with the GPT model a bit,
Yeah.
the API, and then I saw this vector database, Pinecone. They can create vector embeddings of your own text documents, basically.
Okay. Yeah.
So they create the embeddings for you.
Yeah.
But they don't know the embeddings space of GPT.
Yeah.
And apparently it works to put their embeddings into the model, and then it knows what the documents are about. How does this work? Because the embeddings are completely, or are embeddings in general?
What's the embedding API?
Of Pinecone. It's a vector database, and you just shove in the documents,
Yeah.
and it returns an embedding
Yeah.
of the documents.
Yeah. With what kind of model?
Ah, you think it's the same?
Well,
Oh, that could be.
maybe.
Okay, I will check this.
Me-
You know Pinecone?
1 second. I'm just 1 second. I want to pause the recording in the break, but
I can also
Not
look
sure
it up
how.
and get back to you later. It's fine.
oh, I found. All right, let's continue. By the way, can I get a show of hands who here hasn't tried GPT yet? It's pretty. It's 0%. That's the impressive thing. All right. Anyone who hasn't tried GPT-4 yet? All right, that's at least a couple. Good. Good. All right, now I'm gonna introduce just 2, maybe 3 papers which combine GPT and X and other models. This is a big space, so I'm just again providing some examples. Now, one example that you also saw in the projects is the model or the paper called Socratic Models Composing Zero-Shot Multimodal Reasoning with Language. The main reasoning is that you can easily compose models, multimodal models, if they have some modality plus language. And then within this language domain, you can do stuff with GPT-3. And so all these models can interact together. So if you have a model that goes from audio to language and you have a model that goes from image to language, then you can have a model or like a joint pipeline that goes from audio to vision, basically, just because language is a common language, so to say. So for example, in the case of image captioning, what you can do is you can go from clip to GPT-3 to clip, and it works as follows. So in gray, there's a default template shown, and yeah, you provide different kinds of image types, so photograph, comic, or sketch, or all of these things, a number of people you know also, like you simply pick from a selection, and then you ask Clip what's the most likely. So if Clip is seeing 3 people, or if Clip is seeing 5 people, if Clip is seeing a photograph, or if Clip is seeing a comic book strip or whatever. And then if Clip is seeing all of these objects, you simply have a giant list of that, and you ask it what's the most likely thing, right? And then you add this gray part of in this image type that you got from earlier, you add a creative short caption I can generate to this image is, and then you give this whole thing to GPT-3. So now that Clip has filled in the blanks, you provide all of this text simply to GPT-3. And GPT-3 comes up with a couple of captions. So you don't just ask it to make one caption. I mean, then you would be done already. But you can even improve it by generating multiple captions and ask Clip to pick the best one. Yes. So then, for example, you can input this image, and you can get a caption that reads, "This image shows an inviting dining space with plenty of natural light," which is definitely a nice caption, and is certainly better than what you had previously. This image is a photograph. There are no people. I think this photo was taken in a room, house, or living room. I think there might be and so on. Instead, you get this really natural sounding caption because you basically ask GPT-3 to make it more natural sounding. Here's another caption and image. And the paper goes beyond that. It also uses models that align audio and language. It also includes user interaction. It includes much more than that, but this is just the generic example. And I think this idea of using GPT-3 to do a bunch of things that are sort of common sense makes a lot of sense. This work I just want to mention very briefly. It's sort of also a multimodal model, which has a vision path and a language path. And usually this has been done like in a cheap way. You just train it in a contrastive manner, for example, to align. But then if you add strong language models like GPT-2, you see like these improvements in performances. So whenever you have a text model in your pipeline using bigger models that contain all of this useful knowledge is useful. Just as a side note, more interestingly or more concretely, this other paper does the following. So the goal is to recognize different objects, and sometimes Clip is not very good at distinguishing, for example, between a Dalmatian retriever and a golden retriever, let's say. So what you can do is you can ask GPT-3 for useful visual features. So you can ask, what are useful features for distinguishing a Dalmatian retriever in a photo? And then GPT replies with, you prompt it with this answer. There are several useful features to tell there's a golden retriever in a photo. And that's what you provide as a prompt. And then GPT-3 answers with, let's say, 5 legs, golden fur, whatever, nose, floppy ears, and so on. And then you do this for all the categories you have in your data set. So now you know how to recognize these different categories in a sort of more detailed manner. And know in quotation marks, because GPT-3 can also hallucinate things and say, you recognize a golden retriever by, I don't know, wearing a golden chain or something. But it mostly doesn't. And then you can use these new, more fine-grained features for Clip. So now you can see what kind of parts are visible. So for example, in the case of an airliner, you can see engines mounted on wings, landing gear with wheels and tires, large metal aircraft, a fuselage with a pointed nose, wings and a tail fin. All of these are very useful for figuring out that it is actually a plane and not a bus, for example. And then you simply do something smart about aggregating these. I think they just average these. And then you get the maximum, you basically get the argmax again as a prediction, and it works much better than CLIP's zero shot. So in this case, you've improved CLIP's classification capabilities by asking GPT-3 to give us a bit more context, and then providing this sort of context is not in the sense earlier, but a bit more visual things to distinguish, and then applying that. And this paper is in iClear 2023, so it's officially published in May, basically. But it has been out as a preprint for a while. So of course, there's a lot more, but also the question is, how will you combine language models to make something new? And I've also chatted with some students in the break. So I know multiple student teams have been assigned to sort of the same paper, which is completely fine. We'll contact you and we'll figure out like which student team does which project. You can of course also come up with your own direction. Maybe we'll add 1 or 2 directions as well, but yeah, we'll contact you for that so you can start earlier on the projects than after the in-person tutorial. Question? Yeah. Yes.
In the model on the right side and also in Socratic models, both of these cases, we are designing kind of a template to get request features, which is basically kind of creating some kind of feature extractor kind of thing for from GPT that we're going to use in the next step.
Yes, pretty much. Yeah, we're trying to, in a way, what you could also say, we're using GPT-3 as a database that we can tailor. Like, I mean, it's not the first time that people have done something like this. People have used Wikipedia, people have used other like handcrafted data sets and tables of like, there's tables that say like, for example, if you want to recognize this bird, look for a yellow part here and green part there and so on. But GPT-3 gives you a lot of, or like language models in general, give you a lot of flexibility here. Any other questions? Yes?
In the previous slide, how would you generate this fill in the gaps text in the first place, then for GPT-3 to fill it in?
Have a beer and get creative. Yes. That's sort of the funny part. About a lot of these research directions. Like, if you, for example, change this from I'm an intelligent image capturing bot to I'm a super intelligent, maybe it will perform better, right? So it's somewhat annoying, but it's also, there's some things that you can do that whole papers have been written on just changing the prompt to improve the performance by a lot. So this is also a bit of being creative. And the other thing is, of course, all of this comes somewhere from the training data. So, for example, if you know that this is a common thing that is, for example, if you added like ELI5, explain like I'm 5, then just adding this to whatever you put into GPT-3 will give you like a really simple version of the text. And you wouldn't know this if you hadn't been around in the internet, basically. So I think, yeah, being around in the internet might give you some good ideas of what to try as well. But other than that, it's just experimenting and always making sure to evaluate quantitatively would be my advice, because it's easy to get blinded by singular examples that happen to work well.
And the captions, are they just generated, or do you use Clip to kind of condition GPT-3 on this whole?
So you use, first of all, you use Clip to basically get the green stuff out, and then you put the green stuff in the box. Then you have the text. This text you throw into GPT-3, And GPT-3, it's not deterministic, or like the way the next word is predicted, it has probabilities, right? So you can always pick the argmax, and then once you put this in, it will only generate one caption. But actually, because it's a softmax, you simply sample from the softmax. So sometimes it won't pick this as the first word, but it might pick something else as the first word. And then the next word might change as well. And so you can sample all kinds of different captions. If it's very clear what comes next, then there won't be that much variance. So you can actually control this with like the temperature of the softmax. So yeah, and this is true for any language model. You can always sample with different temperatures. I think here next, yes.
Another question on how are we quantifying the performance of the captions? Like when we say it's getting better,
yes.
What do we do?
Yeah, good point. So there's data sets which have captions. These data sets often have multiple captions. And then you can, for example, try to find, okay, how close is it to these captions? But generally, you're right, it's not the best thing, because you can caption an image in like so many ways. Plus, with these sort of things, we don't know what was inside of the clip data set. I think they write somewhere that they didn't include Coco, but we also don't know what's inside GPT-3. Maybe GPT-3 hasn't, well, obviously it hasn't seen images, but maybe it has seen the exact correct captions. And all of these things are somewhat problematic, which people are not ignoring, but it doesn't, like if you can show that this works on all kinds of data sets, then people worry less, for example. So like in this case, having quite exhaustive evaluations matters a lot. And for example, in the GPT-4 paper, they also, or like in GPT-3 as well, they test a bunch of things that their training data set didn't contaminate or wasn't contaminated by the data sets they want to test on later on. Yes?
Yeah, I'm not sure I understand how you get image type out of a clip.
Yeah. Well, it's the same as with everything else, actually. So let's start with the number of people. That's quite easy. You have, let's say, 0 to 10 options, or let's say 0 to 5 options. You can have no people, 1 person, 2, 3, and more than 4, or something like that. And you simply embed these sort of things in the text encoder. And so you have 5 different text embeddings. And then you put the image through it and you pick the argmax. And then you know there's 2 people.
Yeah, so you need to generate yourself all the answers to like places and do a bunch of.
Yes.
Yeah, okay.
And these are sort of easy to generate in a way. I mean, I'm not sure exactly what they did for the objects. You have to check the paper in more detail. But for image types, there's only so many. For number of people, easy. Yeah.
Cherry tree would be like, you need to go through a lot of different objects to get to a cherry tree. So yeah, they probably use a lot of computation or.
No, you don't need a lot of computation at all. Like, for example, let's say you want to differentiate. I mean, if you look around, there's probably like 1,000, maybe 5,000 common objects around us. So you just get the text embeddings of these 5,000 objects. Like, so not the text embeddings of the object, but of the text on this image, there is object. So you get 1,000 sentences or 10,000 of these. You get your text embeddings. So you have 10,000 text embeddings. Now you get the image embedding. And now you check, okay, which text embeddings is this image embedding closest to? And it might be close to cherry tree. It might be close to people. And it might be close to, I don't know, food maybe. And then you know what's on the image basically. But knowing what's on the image is still different from writing a nice caption. And that's why they have GPT-3 make a nice caption out of all of this basically. Yeah. But yeah, you don't need many forward passes at all, basically, for this. Like, I think there is a cherry tree in this image. You compute that once, and it's true. You don't need to compute it again for all of the different images, right? So just like in the assignment, the text embeddings you only need to compute once and you can store them. Any other questions? All right. Right. But that's of course not all. So this was, well, we can combine them, we can use contrastive, but there's other text image pre-training methods. So for example, I don't know if you know this, and I'm not sure whether it is from the New Yorker captioning context, but there's this thing where you have comics and then you're supposed to come up with a caption yourself, and like you can come up with all sorts of funny caption. And yeah, so it's, yeah. You can do captioning as a pretext task is what it's meant to tell you. So there's this paper called Align, Scaling Up Visual and Vision Language Representation Learning with Noisy Text Supervision. So the task they tackle is that, well, if you simply look on the internet and you look for images with captions or images with alt text, they're mostly not particularly good. So for example, if you take the middle one in the first row, thumbnail for version as of 21/57/29 June 2010. If you train your vision language model on that, it's not gonna be great. And then the other one in the bottom right, St. Oswald's Way at Shops. It probably also isn't super helpful for the model to know what St. Oswald's Way is, because it's just gonna occur twice or 3 times, but rather you wanna have it either not use it, or maybe it should just be a street with cars or something. And yeah, you can see all kinds of trouble with this. That's why in the title, they also have noisy text supervision, because the text is extremely noisy. The images in this case, or in most cases on the internet, are not very noisy, right? They're not edited. There's nothing crappy posted on them, or like like letters on them, like memes. I mean, nowadays you have more memes, but you can easily recognize and remove them if you don't want them. So what they do is they filter based on images. That's pretty easy. They remove the ones which are too small and remove the ones which for some reason they found have like more than 1K different captions. So it could be just images which are stock images and used for various purposes. Then they filter on text, which is their main thing. For example, they filter image text pairs with alt text that have more than 10 occurrences. For example, 1920 times 1080 as a dimension, which are too short or too long, or contain very rare words or very rare letter combinations. So that could be a hash or just a file name or something like that. What they end up is, and they do a bunch more, what they end up with a data set of 2 billion image text pairs. And they also show that you can actually combine the text embedding and the vision embedding to then retrieve similar images. So for example, you can get the text embedding, you can get the image embedding for these 2 things, so Eiffel Tower and the word snow. And then you look, okay, given these 2 things, what are the closest images that we have in the database that live when you add these 2 things together? And then you indeed get an Eiffel Tower with snow in the winter back. One thing about this is that they train on 1,000 TPUs, which is a lot, and their batch size is 16K. But otherwise, it's pretty easy to understand, at least. Like they train simply in a contrastive manner, just like CLIP. The only difference is they have a noisy data set, and the noisy data set is much bigger, but yeah, they obtain pretty good performances. Then Coca. In this case, the Coca version that I have in the collab link here is not the official one, but a reproduced one. All right. So Coca stands for contrastive captioning, and this model again, or this model now, is doing a captioning loss. So at the first stage, and that's the yellow part, you can see the image encoder and the unimodal text decoder. So unimodal text decoder, that could simply be a GPT model or all kinds of models. And what you have there in yellow is a contrastive loss. So that's exactly the same as CLIP or as Align. Now the next part is the captioning loss. So this is more interesting. So now the model is not only trying to associate the image embedding and the text embedding together, but also try to predict the caption from the text embedding and from the image embedding. And if you look at this at first, you might think, okay, well, you might as well cut off the image encoder and text comes in and text comes out, right? So it should be trivial, but that's where this sort of causal masking comes in. So obviously you don't want that, but instead, because it would just, you could, the text encoder could otherwise just be identity. But instead what you want is you first put in the text decoder, you put in a starting sentence token, and this one needs to get mapped to the next word. So in this case, the caption is 2 dogs running in a field, and you want to have the starting token be mapped to the word to, the word to mapped to dogs, the word running mapped to in, and so on. And if you mask it correctly, then it never knows what comes next. So it has to figure out how to start the sentence based on the image inputs. And that's where you have this cross attention mechanism going on. So instead of inputting all the image encoding outputs into the transformer and basically having a lot of queries into the transformer, you simply let the queries, which are the individual tokens that you put into the text decoder, be able to look at the image features, but otherwise the image features are not used. So this is called cross attention. And I think we've had this in one of the lectures as well. But it's simply, the same attention mechanism, except that you only have them look at the image queries here. Right. They also train quite large models. So their largest model is 2 billion sized. And they achieve pretty good performances, of course. Let's see. So, right, one thing that, as you saw earlier as well, and starting from these models even more so, is that these models have various ways of how you use them. So obviously you can simply use an image encoder and then, for example, do classification, like fine-tuning. You can figure out whether these two things are aligned. That's sort of the clip use case. So you can do zero-shot classification, but you can also do image captioning, and you have this multimodal representation space going on for you. Right, it works well, as you might have expected. And we'll go to these use cases in the next works, basically what you can do with these multimodal feature spaces. For now, I want to briefly also introduce ClipCap as a very simple work that can do image captioning. So ClipCap basically takes Clip's visual encoder. So you do that and you get visual features out. And what you then do is, in the easiest version, you further transform the visual embeddings in all kinds of ways. So just MLP, for example, to match the input space of GPT-2. So GPT-2 has an input space, depends on the size of GPT-2, but let's say 700 dimensions. And the Clip's visual output is, let's say, 500 dimensions. So you just have 2 MLPs, which gradually transform Clip's visual embedding space to the GPT-2 input space. It doesn't even need to be a single GPT-2 input token, but it could be multiple. So in this case, you can see these 4 prefix embeddings. So you basically transform the visual part simply into a word in a way. So you don't map it to explicit words, but you simply map it to the space that comes directly after a word. So in language models, you have obviously the words, but then every word is immediately transformed into, or every token is immediately transformed into a vector. And in this space, we map the image basically. So the GPT-2 model can now deal with the image part as if it's working with words basically. And you can fine-tune GPT-2, or you can keep it frozen. If you keep it frozen, you need this adapter part or mapping network to be a bit more powerful. In this case, they use a transformer, which is this part. And Now, these sort of models we would call visual language model, because it's not a vision language model, because vision language model we would say is something like CLIP. But here, what we have is it's a language model that can also treat images as language, basically. So people are calling these visual language model. It's not super important what you call things, obviously, but it is a subtle difference and shows that language models are extremely flexible. They can deal with, obviously, language as input, but if you map images correctly, they can even deal with images as input or audio as input or everything as input. So that's quite interesting. Another point that's interesting, of course, is that, as I said, you can keep most of the stuff frozen. And I mean, this is just using GPT-2, but still what they report is training just for 80 hours on one fairly old GPU. So that's quite nice. And what you're doing is you're leveraging the power of GPT-2 for captioning in a fairly simple, easy way. What I didn't write here, of course, is that you need some data set to train it on. So you need loss, you need gradients for the mapping network. You can only get gradients if you have a data set with captions. So that's very different from the Socratic models paper. So for the Socratic models, there's no training, no gradients whatsoever, right? Here you need some gradients to train the mapping network, right? So we have this clip cap. We just talked about it. Are there any questions before I go to the questions? Yes. Yeah. So the caption tokens are simply fixed inputs, like paddings, spaces, because GPT-2 outputs however much it wants, basically. And the prefix embeddings are the ones that you learn. So for example, if GPT-2's input size is 700 dimensions, the mapping network, for example, outputs a 70,000 dimensional vector, which you then transform into 10 700 dimensional embeddings. So and then it's basically 7 inputs to the GPT model. And then, yeah, that's the part that you learn. The rest is fixed. And you train the blue part and the gray part in a manner that it learns how to generate good captions. And GPT-2 already knows how to make proper sounding English, basically. So there's not too much adaptation going on. You just need to provide the input in a manner that steers it towards generating a caption that matches this. All right, so then a question from me. Why didn't they use GPT-3? So one answer is likely it requires too many forward passes, so it would be too expensive. 2, GPT-2 does the captioning job well enough, so no need for GPT-3. 3, it wouldn't work. All right, so you know the drill. So on the count of 1, 2, 3, you point out 1, 2, or 3. Right, everyone knows what they want to answer. All right, 1, 2, 3. Right, and 1, 2, 2, 2, 2, 2, 3. Lots of 2s and 3, some 1s as well. Well, 1 is sort of true, but not the point. I mean, yeah, it would be expensive, but 2 is GPT-2 does the captioning job well enough, so no need for GPT-3. I would say we have to test it, otherwise we don't know, right? So what remains is sort of point number 3. Point number, or like likely it requires too many forward passes, so it would be too expensive. Well, that's not the reason why we cannot do it, or why they didn't use it, I would say. The main reason is it wouldn't work because GPT-3 is only available as an API, but we talked about the gray part requiring gradients. If you only get the output, you can throw something in GPT-3 and you get something out, but then you can compute the loss between the something that comes out and what you wanted it, but you won't be able to backprop the gradients through the weights of GPT-3 because you don't have the weights. And that's why these open source models are hugely important, like Llama and OPT and GPT-Neo, and all of these models that we can actually download and actually use on our servers. And then you can actually use GPT, like much larger models. Another note is also, if you keep these language models frozen, you can do, there's a lot of libraries that allow you to use them on very small GPUs as well. So I've heard like you can use billion-sized models on MacBooks, for example. So there's a lot of optimization that you can do on language models if you keep them frozen. So one trivial thing would be, instead of having, let's say, float 32 weights, you can have integer 8 weights. So that's network quantization. And there are some methods that work really well. All right, question 2. Why is the transformer adaptation and freezing GPT very nice? 1, there's no catastrophic forgetting in the language model. 2, the language model can be made very efficient. 3, transformers are faster than fully connected layers. And 4, the number of parameters doesn't depend on the number of clips, visual output size. Right? Which question is wrong? Why is the variant not nice, basically? Or if you have 3 hands, you can also answer the question. But okay, I mean, yeah, so I've pretty much answered it. That's why I'm not going to ask them. Yeah, there's no catastrophic forgetting in the language model. If it's frozen, that's nice. Language model can be made very efficient. I sort of said that too early. What's not true is transformers are slower, obviously. Transformers include fully connected layers, so obviously they're slower. Number of parameters doesn't depend on the number of clips, visual output size. True, but also true for MLPs, right? It's kind of like a fully convolutional thing you have going on. So the MLP just is applied the same at every visual output thing. All right. Next work, Blip, creative name. It's called Bootstrapping Language Image Pre-training for Unified Vision Language Understanding and Generation. And the models are out there. All right, so in the first stage, and you sort of sometimes have to abstract a bit away from all the details of what's happening in there, but you just look at the broad sketch of things. So you have an image, you can see it's petrified, so it's probably you're probably dealing with a vision transformer, and then you have this first part, ITC. You look at the caption and you see it's image text contrastive learning. All right, so you know this kind of like clip. And you see the text is there, you add some sort of token to the text encoder. You see, okay, probably you take the CLS token out and you map it to the image part and you simply do contrastive learning. That's easy enough. Then you look at the rest of the figure and you think, oh my God, what's this? And then you see, okay, well, the image embedding simply goes again in some sort of cross-attention module. Well, we've sort of had that before. And then there's this ITM thingy going on. And then there's another thing which looks exactly the same. And then there's this LM thing going on. All right, so ITM, what is it? They sort of added this new loss, which is called image text binary matching, which is a really trivial loss. It's sort of a softer variant of contrastive loss in the sense that you provide, it's a binary loss. So you simply check, does this caption match this image? Yes or no. So for the diagonal, it would again be yes. So it would just have to be a 1. And for the off diagonal, in quotation marks, elements, it would be 0. So that's pretty easy. And then the LM part, which they call language modeling, is simply this captioning again, and which is done in the autoregressive manner, just like in the previous work, which was which one was it? Coca, where you basically always predict the next word, next word, next word. That's the autoregressive part. So right, so this work does also contrastive learning and does captioning and has this ITM part, which you can use, but is mostly just useful for training. And what they do with this, and that's why it's called bootstrapping, the bootstrapping's in the title, is they use this for iterative data filtering and gradually expanding the data set with synthetic captions. So if you have a model which was trained first on a very clean data set, you can then use it to caption a data set without captions, for example, if you use only the samples where you're sure of. That's the basic idea. And then you use this new synthetic caption as a ground truth to train to train the same thing, like a clip model. And they show that synthetic captions actually work pretty well. So this thing has various usage modes. So for example, the most trivial thing is, okay, image caption matching, which is sort of this ITC, I think was a part, ITM, that's how they called it. So does this caption match this image? Okay, yes, no, that's kind of useful, but not super useful. The other thing is you can do image captioning. That's way more useful, and they evaluate it on a bunch of things. They can also do text and image encoding and text decoder. They can use these in various ways. So one thing that's very interesting is you can use it for VQA. VQA stands for visual question answering. So you input the image into the image encoder, you add this encode token and the query and the question. So in this case, for example, would be, what color is the t-shirt that the guy on the left is wearing? And then you ask the model to provide the answer, basically. That's the most interesting case, but you can also do this dial, which is like a visual chat test, basically. So what you do now is you have an image and you add some sort of text again, and you ask it to produce, okay, in this case, you ask it to produce what answer would fit, whether this answer fits as an after this sort of history, or that answer fits after this history. We'll go into these two here now. So VQA is, for example, the following. So you have these two images. One question might be, which object in this image is most related to entertainment? In this case, you put by TV. How many road vehicles in this image? Okay, 3. These would be answers. This data set has been around since 2015. There was a paper coming out, or that came out, that argued, okay, probably something like Q1, you might even be able to guess without the V part. So you like, okay, there's not that many objects related to entertainment. It's not like the average image has like a, I don't know, Nintendo console might be another one, but not that many. So what they did is they showed that actually you can solve this task pretty decently if you simply use a language-only baseline. And the first baseline, the prior, simply picks the most frequent answer in the training data set. And the other one, basically just trains a language model to answer. So this wasn't quite as good. So people nowadays use a other version of VQA called VQA version 2, which basically has balanced answers. So for example, and slightly different things. So for example, they have how many road vehicles in this image. They would have equal amounts of images in the test set, which have 3, 4, 5, 0, and so on. And that's why like just learning language will give you not a particularly good result if you do that. The Vistal part looks like this. The task would be, you have an image and you have some sort of fake chat history, basically. A dog with goggles is in a motorcycle sidecar. Is the motorcycle moving or still? It's parked. What kind of dog is it? Looks like a beautiful pit bull mix. What color is it? So in order to understand it, you really, well, not really, but you sort of need to understand at least the last part, and you need to be able to look at the image, and then you need to be able to answer this. Right. And I haven't gone too much into detail how now you can make this sort of chat-like thing, because that's sort of part of the next one. And we're going to be talking about extending context and then emergence. Although emergence might be the one which we'll cover in the next lecture. Are there any questions so far? Right. So then next we're going to look at BLIP2. Bootstrapping language image pre-training with frozen image encoders in large language models. So now the part is about having frozen models, really, which is quite nice. So in this case, both the language model that we'll use and the image encoder remain frozen. In this case, the first stage is basically you take a pre-trained image encoder in this case, and also in the case of Blip, they also use clip. So Blip outperforms clip because it uses clip in there as well. For example, for selecting the data points. In this case, for example, they use as the image encoder the clip image encoder, which is just a very good image encoder. And then they train like another transformer on top in a similar manner to the original work Blip, in a contrastive and captioning and all of these manners. And then what they do afterwards is they take this and then they throw a very large language model on top of it to now have this captioning task as the main thing. And now previously in this Q-former and the Blip loss, they had some language model, but this one was fairly small. And now they use very large language models in the billions. And now these large language models are much better for captioning. And if you use this sort of two-stage pipeline, this Q transformer already knows how to integrate text and the image in order to generate decent captions. But then in order to generate really well captions, you can use this already aligned space and put it into the large language model. Well, starting from there and fine-tune it further to generate pretty good captions. As with Blip, it uses clip. It uses very large language models for this captioning part. And now it has these sort of nice capabilities. So now you can input an image and a text and ask it to generate the next text. And then you can input all of this, what it has done so far. So the image and the text and the answer, input it again into the model, and it will produce the next answer and so on. And the reason why we can do this is simply because now again, this is also a visual language model. So you can simply, instead of feeding a sentence, which might be 10 words, which might be in turn like 30 tokens, so words are further split into tokens, not too important, but instead of feeding 30 words into the language model, we can feed in 30 words and 2 visual words, or we can feed in 2 visual words, 50 real words, 2 visual words again. So because the images live in the same space as language, this is all the same to the language model that's sort of working in the background, which makes for really cool demos and really useful applications. But in the end, all the model is doing is a language model that's sort of predicting what comes next, essentially. But you get these advantages if you map the image space to the language space. And it does this model does this by having frozen models. And what they also show is that better image models and better language models both lead to better captioning performance. Yes?
But the responses are always going to be language, right? Not the visual. Is it possible for us to use the same process in reverse and not generate images, but rather retrieve images?
Yes, this one. Yes, exactly. So that's what this paper does. So they call multimodal generation. It's not as generative as other works, but this is precisely what they do. So this model can not only output text, but can also say, here's an image from my database, basically. The model is called Fromage. Reminder, catchy names matter in this field because there's so much going on. What they do first is they train with captioning loss. So that's kind of like ClipCap. What they, however, do is sometimes, and that's why it's very weird. So captioning, you would simply imagine as like image, and then you have the caption, and you have your loss. And sometimes they append another example here, and the model sort of needs to ignore this second example and simply, not ignore, but output the caption of these 2 things. And they call this augmentation. It's kind of like a data length augmentation. They do 50% of the time. This, they show works well. And the reason why they do that really is because it sort of mimics this in context like or chat history like learning, right? So even though they have nothing to do with each other, the model sort of needs to look at or needs to get used to being able to see two visual words in a single sentence if it needs to do that at test time. And then in addition, they have this retrieval or contrastive loss. So how they manage to be able to provide images is basically they learn another token, they call the retrieval token, and add it to the language model's library or like dictionary, sorry, not library. So what this means is the model can output hello or can output world or can output red. And red is now this token that they use. And this retrieval token actually is different depending on what you want to do. And if this is returned, it simply picks up the image that's closest in the database and will return it. We'll go back to that in a bit. So it looks like this basically. So you can play with it and you can ask it to answer only text, and then this last gray box is there, show me an illustration of a beaver, and it returns an image. And then you can ask it, okay, return to me something different, and it returns images. And actually, and that was the last figure here, what this one shows is that if you add multimodal context, so if you just provide a caption, and here you're trying to find the right image, so to say, in a database. If you provide one caption, it works like this. If you provide more captions, it works better. If you provide a similar image, it works even better at finding the right images. And so multimodal context, so having this sort of chat history with images in a way, helps with this task. And this model, because all of these models, or the visual model and the language model, they are frozen, trains quickly, so 24 hours on a single GPU. But what you can do is quite cool. Here's a couple of examples. So for example, with a motorcycle plus X, the X could be at the lake or at the beach and at the forest. It's kind of like the Paris and snow example we had. Oh yeah, in the paper, there's just a bunch of examples. So I'm not gonna go into all the details, but definitely worth a read, even if this is not your project paper. And it's, yeah. And then there's the Flamingo paper, and I think that's probably the last one for today. Let's see. Yes, yeah, that's right. What the Flamingo paper does is it's another one of the visual language models. It uses a frozen language model and a contrastively pre-trained ConvNet. So the vision encoder is also frozen. However, in the language model, they add these violet blocks, which they train from scratch. These are initialized in a way that they first do not interfere with the language model. So you can see they are sort of put in between the language blocks. So if they are randomly initialized, they would completely screw up the language model. So they're initialized in a way that they first don't have any effect. And then notably, this paper and related papers nowadays, they train on web pages. And web pages, they include, or like the data set they use, include multiple images with some text in between. So perhaps think of it as like Wikipedia articles or personal blogs and stuff like that. And in addition, they train with 1.8 billion text image pairs from the Align paper. And in addition, they train with video text data. So they train with a bunch of things. They here use this perceiver resampler to produce a fixed context size. So you can have the history be as long as you like, because every time you put it through, the perceiver makes it a fixed length, basically. And yeah, it has extremely strong performance and has really, so all of these tasks like VisDial, even Coco, Latex, image retrieval. So a bunch of very different tasks perform extremely well thanks to this, first of all, huge language model, 80 billion language model. At the time, best language model, really strong vision encoder, and then this huge vision language training part. So here I should now add a link. So this model has now been trained in an open source manner as well, thanks to the Llama language model, which has recently been released. And so we can actually play around with this. I'll add a link to the slides later. It's not as good as a proprietary one, but it has similar capacities. It was trained in a similar manner. So it's quite cool. And I'll actually end with this slide. So this is the last paper for today. And this model has this as a first figure. So it's very, very similar. So don't be fooled by the emojis. Emojis are just language as well. So treat them like characters basically. And then the model can do this basically. And there's this EOS, which stands for end of sentence. So basically the model outputs this and then it stops producing. That's sort of the typical way how you stop with sentences. These are actually cherry-picked results as they write themselves. So let's not be fooled too much. But what they do is, what is quite nice is they basically have a frozen language model again, but they train the vision encoder from scratch here, simply with the task of captioning in a causal manner, as before. You can see that here. And what this now is you might see the similarity here. This is in context learning, right? So we are saying it probably hasn't learned it hasn't been trained for the task of figuring out what inventor this particular object is, but you provide an image, you provide some few shots, and it can now solve the query. So what this is it is multimodal in context learning. And so this is where we'll continue the next time with in context learning. What is it? What are the details? And how does it apply to multimodal learning? All right, then thanks and see you soon.